Let's analyze the second price auction. Let's suppose there are n bidders, and for each bidder I, the valuation of the item that's being auctioned is VI. So that's what the ith bidder thinks that the item is worth, and that valuation VI is some number between 0 and 900. And that's true for every bidder I. And only bidder I knows what VI is. So this is going to be a Bayesian game. We'll let BI be the bid that player I submits. So for each player I, a strategy is, as a function of VI, what bid BI should you submit? The way the auction works is that given a profile of bids, which we'll denote by lowercase b without a subscript, so b would be a bid for bidder 1, bid for bidder 2, all the way through a bid for bidder n. So given a bid for every player, I wins if BI is bigger than BJ for all j not equal to I. So if I has the highest bid, I wins. Or if I is tied as the highest bid, so if I has at least as high a bid as anyone else, and there exists some j such that BI equal to BJ, and I was chosen at random from the group of bidders bidding the same as I. So from the set of bidders k, such that the bid of bidder k is equal to BI. So this is the set of all the bidders who submit the highest bid, and they're tied, and I is chosen randomly from that set. So the winner is chosen randomly. All the other bidders lose. So what is a bidder's payoff given a profile of bids? Player I's payoff at the profile of bids B is if I wins his valuation minus what he pays for it, which is the highest losing bid. We'll represent that by B sub parentheses 2. Sometimes we use that for what we call the second order statistic, so it's the second highest of all the bids. So that's the payoff if I wins. And if I doesn't win the auction, then their payoff is simply 0. One thing you'll notice that I haven't told you, if I go back here, is I haven't told you what the distribution of these valuations is. I haven't told you what the probability that VI is 3 would be. I haven't told you the probability that VI is 81 or 395. We don't know what those probabilities are, and I haven't told you that yet. So it turns out to analyze or to find a Bayes-Nash equilibrium of the second price auction, we actually don't even need to know that. That's one of the nice things about the second price auction is that we can prove the following result. No matter what the others bid, it's a weakly dominant strategy for you to submit a bid equal to your valuation. And because of that, no matter what the distribution of other people's bids are, or other people's valuations are, you're still at least as well off bidding your valuation as anything else. So if everybody bids their valuation, that's a Bayes-Nash equilibrium. Everybody's best responding, because you can't do better than bidding your valuation. So the really nice thing about a second price auction is that we can find a Bayes-Nash equilibrium without having to assume anything about how the valuations, in this case, the valuations are the types. So without assuming anything about how the types are distributed, we can solve for what the Bayes-Nash equilibrium is, which is that everybody just bids their valuation. So let's write that down and go through a proof of why that's true. This proof will look familiar to you because you've seen a homework problem that's very similar. So formally we'll write that down as follows. No matter what everybody else bids, so we'll call that B minus I is at least as well off bidding BI equal to VI than any other bid BI prime not equal to VI. So UI of BI B minus I is at least as big as UI of BI prime B minus I, where BI is VI and BI prime is not VI. So this has a very important implication that bidding BI equal to VI is a best response to everything. It's always a best response. So it has to be a Bayes-Nash equilibrium then for everybody to bid their valuation, because player I doesn't need to know anything about the other player's valuations to know that bidding their valuation is always going to be a best response. So if bidding their valuation is the best response no matter what the others' bids are, then no matter what the valuations are and what the bids are of the other players, the best thing to do is to just bid your valuation. So let's prove that. We'll consider 3 cases. The first is where if we look at the bids of the other players, look at all j not equal to I, and we look at the bids that player j submits, and we look at the biggest of those, and VI is bigger than that. So if we drew a picture, it would look like this. We have VI up here, and we have BJ here, and all the other bids are below BJ. If I bids BI equal to VI, so if he bids his valuation, in fact, if he bids anything above BJ, then I wins. So for any bid up here, I wins. And what's i's payoff going to be? Well, i's payoff is going to be his valuation minus the second highest bid. So it's bj. So no matter what I bids, as long as I bids more than that, he wins and gets the valuation vi, but only pays bj. Again, all of the bids that I could submit that are strictly higher than bj will yield a payoff of vi minus bj. And that includes vi itself. However, if he bids bi equal to bj, then I only wins with less than 1 probability, but when he wins, he still gets this payoff. So his expected payoff is vi minus bj if he wins times probability that I wins, and this thing is less than 1. So his total expected payoff is less than vi minus bj, which is the payoff he would get if he bid greater than bj, including vi. Finally, if he bids some bi less than bj, then I loses for sure and gets a payoff of 0. Let's remind ourselves that in this case, vi is strictly higher than bj, so this is a positive number. So in case 1, I cannot do better than bidding vi. Bidding something other than vi, higher than bj, you'll do just as well as vi, but you can't do better. So the highest utility that you can get is vi minus bj, and bidding your valuation gets you that. So in case 1, bidding bi equals vi maximizes i's payoff. So let's look at case 2. This is where vi equals the highest of everyone else's bids. So if we maximize over j not equal to I, bj, that's equal to vi. So that's the second case we consider. In this case, no matter what I bids, i's payoff is going to be 0. If I wins the auction, for instance, they could bid higher than vi, and they would win the auction, but they would pay their valuation. So if I wins, he gets a payoff of 0. If I loses, he gets a payoff of 0. Thus, in case 2, everything maximizes i's payoff. So in particular, bidding bi equal to vi is also optimal. Finally, there's a third case where vi is smaller than the highest of the other bidders' bids. Now, if I bids some bi higher than bj, so picture looks like this, the highest of the other bids is bj, vi is down here. So if I bid something that's further up, bi up here, then I wins, but winning means you get a payoff of your valuation minus the highest losing bid, which would be bj, which is higher than your valuation. So vi is smaller than bj, so your payoff is negative. If I bids bi equal to bj, again, I wins with probability greater than 0, so i's expected utility, probability that I wins, times vi minus bi. This thing is greater than 0, and this thing is less than 0, so this whole thing is less than 0. Finally, if I bids bi less than bj, then I loses and gets a payoff of 0. This last case includes vi. So again, even in case 3, bidding bi equal to vi maximizes your payoff. The highest payoff you can get when vi is less than the highest of the others' bids is 0, because if you win the auction, you're going to get negative payoff. So by cases 1, 2, and 3, for all b minus I, so no matter what the others bid, bi equal vi yields the highest payoff that I can get, given b minus I. In other words, bi equal to vi is a weakly dominant strategy. And as I pointed out earlier, since bidding vi is a weakly dominant strategy for every player, no matter what the probabilities are for the vi's, we know that it has to be a Bayes-Nash equilibrium for everybody to bid their valuation. And that's true regardless of the probability distribution of the valuations. An important point to note here is that all that we needed to show this is that player I knows what the item is worth to them. We could have had correlations, we could have very complicated ways in which these valuations are distributed, and it wouldn't matter. So this result is very, very robust. Later on in another video, I'll show you how things get complicated when players don't know the valuation. So this is a private value auction, and if players don't know the valuation, but rather they have some estimate of the valuation, where other players have some estimates of the valuation, and the actual value of the item is the same for everybody, but we just have different estimates, that's called a common value auction, and things get much trickier there.